Hello students, welcome back. Let us resume our discussion in section 1. Previously, we went through the definition and some examples of cyclic groups. Now the next topic in line is theorem 1.5, which says a subgroup of a cyclic group is cyclic. Sounds pretty benign and certainly brief. However, it turns out this is a major theorem with a challenging proof, which is a preparation in number theory, namely the division algorithm. Given pair of integers n and m with the divisor m strictly greater than 0, there exists a unique pair of integers q and r such that n is qn plus r and r is greater than or equal to 0 and strictly less than m. Such a pair of integers q and r exist uniquely. That's what it says. Do you remember the terms? Here, n is called the dividend, m the divisor, q the quotient, and r the remainder. As for the proof, well, we covered it in lesson 3 in one of those optional videos, so let's not worry about it here. Let's be prepared to use it, especially these blue and green. Existence we'll take for granted, but then again, how is this related to theorem 1.5? A subgroup of a cyclic group is cyclic. Well, let's paraphrase this symbolically, maybe that'll help. Let's begin with a cyclic subgroup generated by A, and let's take an arbitrary subgroup H from there. The theorem says this H can be generated by a certain element C from H. Our aim is to find such C. But then again, what does it have anything to do with this division algorithm? Let's go back all the way from the starting point. And everything began from a cyclic group generated by A, so everything here can be written as a power expression of A to the certain power. In particular, C can be written as a to the m power, where m is an integer. Now do you see a connection? Previously, this is abstract algebra, looking for a certain element from a subgroup. Now this is number theory. You're looking for an integer. And does this have anything to do with this division algorithm? Well, yes. Exactly how? Well, you'll see. Let's begin the proof, and the proof consists of 3 steps. First, we have to find out the candidate of the generator. How do you define C? In other words, a to the m power? Of course, that comes from finding m. And then we're going to apply the division algorithm on m, and that'll give us a certain conclusion, a provisionary conclusion for step 2. And then we'll work out that provisionary conclusion to get the real conclusion. That is, H is generated by the C, a to the m power. Okay, let's go. How do you define this candidate? Before that, let's make this trivial observation. We started from a cyclic group, so everything is a to the certain power expression. Okay. Next, the simplest possible case when H is trivial, then is cyclic. We have only a to the 0 power. So, when this group is trivial, then it's cyclic, no problem. So let's assume H is non-trivial, so that it has non-trivial elements. Everything must be a form of a to the k power, so it should be a to the k power. And also its inverse must exist, a to the negative k power, because H is a subgroup. And also, we assumed H is non-trivial, and then we found out non-trivial element, a to the k power. So k cannot be 0. If that's 0, then we have E. We found that non-trivial elements, so k is non-zero. So k and then negative k. One of them has to be strictly positive. And without loss of generality, we'll assume k is positive. Now pay attention to this groundwork because that's going to be absolutely necessary. We define C as a to the m power like this, where m is the minimum of this subset of z plus. We have this condition here, a to a certain power belongs to h. That's precisely what we discussed. A to the k power belongs to h. That's what we discussed. And then k is strictly positive. That's something we discussed too. So this non-trivial element means this set is non-empty. Remember, every non-empty subset of Z plus has the minimum because Z plus is well ordered. If you have empty set, then you don't have minimum. So this process here ensured that this set is non-empty, so minimum exists, and we define m as the minimum. So m is well defined, so a to the m power is well defined, and consequently c is well defined. One more observation. M is a member of this set because minimum is member of the set. So it must satisfy this purple condition as well. Consequently, C belongs to the set H as well. So, okay, we got what we wanted here. And we have to prove that every element of H can be written as a power expression, C to a certain power. How to do that? Let's select an arbitrary element B from H. And of course, it should be a power expression of A as well, because we started from the cyclic group generated by A. And then we have now two integers. N from here, that's an integer, and M from here, which is a positive integer. This came from Z, this came from Z plus. So we can apply the division algorithm. You see, M should be strictly positive. So we get blue and green for appropriate Q and R, which exists uniquely. Same conclusion here. The quotient and remainder exist uniquely so that blue and green. We're going to have to use both. But blue first. We're going to do green later. So let's apply this to b equals a to the n power. And nth power can be rewritten as qn plus r power. Can you read it? Let me expand the font a little bit. Okay, that's going to be a bit easier. So a to the n power is, okay, qn plus r power. So it's same as q times m power times a to the r power using the exponent rule. And that's a to the m power to the q power times a to the r power. And then what is a to the m power? Remember that? That's c. So it's c to the q power times a to the r power. That's what I get. And what did he do this for? Well, b came from h, and c belongs to h. C to the q power belongs to h as well, because h is closed under group operation. And then divide this one away to the other side, and inverse also exists in h because h is subgroup. So if I do that, we end up with this conclusion. A to the r power belongs to h, because both come from h. And I just highlighted in purple, just like this, and please remember, there is a connection. A to the certain power belongs to h. Yeah, right here. That's the conclusion from step 2. Now, how do we utilize this provisionary conclusion in step 3 to get the real conclusion that we want? Let's go. We're going to utilize h to the r power belongs to h, which I just highlighted in purple. And then I claim this implies r is equal to 0. Is that obvious? No, not really. Let's prove it. And we're going to use the proof by contradiction. Remember that the remainder is greater than or equal to 0 and strictly less than the divisor. You see, remember? You have blue and green. We have to use both. Blue we used up. Green, now we are using green. Therefore, if I assume r is non-zero, then r has to be strictly greater than 0. And of course, it remains less than m from the previous condition. Does it help? Well, if I apply this to the conclusion of step 2, which I just highlighted in purple, we get a conclusion like this, which is a contradiction. R is greater than 0. Consequently, we're talking about z plus, highlighted in brown. Now, we prove in step 2 that h to the r power belongs to h, and that corresponds to this purple condition. So what do we have? Brown and purple. We have the very same set where m came from. So r and m both came from the same set, and r is strictly less than m, yet m is the minimum. That's not possible. There goes your contradiction. And what causes contradiction? Well, we assumed r is non-zero. That's the reason. If r is allowed to be 0, then purple is of course always true because we proved in step 2, but we don't have brown anymore. R does not belong to z plus, so no contradiction. So the conclusion, r has to be equal to 0. Remember the remainder equal to 0 means n is divisible by m, and we get this conclusion. You see, n here is divisible by m, so qm. Can you read it? Let me expand the font. So n power is actually qm plus r power, but r is 0, we proved it. So that goes down, and then we have just qm power. And you can rewrite like this, h to the m power to the q power, but h to the m power is c, so we have c to the q power. So what did we get? We successfully expressed b as a power form of c. And please remember that b is arbitrary. So every element from H belongs to the cyclic subgroup generated by C. So H actually is included there. But then again, C came from H as well, so actually we have the other inclusion as well. Consequently, they are the same. H is equal to the cyclic subgroup generated by C. Isn't that the very conclusion that we wanted to prove all along? Yes, indeed. That completes the proof. This process not only completed the proof, but also it gives us a practical formula to find out the generator C, or M. M is defined as the minimum of all positive integers that satisfy this purple condition. A to that power belongs to H. So you can try from a to the first power, yes, then through. Then go to 2, if not, go to 3, if not, go to 4, and so on until you hit something. So if you have sufficient computing power, you can always find a generator like that. So this actually is a practical formula. It's completely algorithmic under the assumption that you have sufficient computing power.